Welcome back students. This is the last video of metals and non-metals, part 3. In this we will learn about the extraction of metals and non-metals. Okay, so we read about the displacement reaction in the last video. In this video also we will learn about its application. Now what are the applications of displacement reaction or uses of displacement reaction? We can extract metals, manufacturing of steel, thermite reactions. Now what is thermite reaction? In thermite reaction is used in welding of railway tracks. In thermite reaction is used for in welding of railway tracks, cracked machine parts, etc. We can occur metals. Okay. Now, how does this thermite reaction takes place? When aluminium reacts with iron oxide, then it forms aluminium oxide and plus iron, molten iron. So this is the thermite reaction, okay, which is used in welding of railway tracks, cracked machine parts, etc. Occurrence of metals. Now, most of the elements we know, especially metals, these occur in nature naturally, right? The elements, most of the metals occur in nature naturally. Either they are in the combined state or they are in free state. But all these compound of metals are known as minerals. Generally, as we know that metals are very reactive in nature, they are in a combined state. Okay, they are present in a combined state, and the compound of metals which are found are known as minerals. But out of them, only few are viable sources of that metal. There are many minerals, but out of them we cannot from all the minerals we cannot extract metal. There are only few viable sources of the metal, and such sources are called ores. Now, like gold and platinum, this can exist in the native or free state, but the other metals, they are generally present in the combined state. I am repeating myself. Gold and platinum, this exists in a native or free state, but the other metals are generally in a combined state. Why? Because gold and platinum, they do not react. They are least reactive, but the other metals are reactive. That is why it is present in a combined state. Now, what are the steps which are involved in the extraction of metal from the ore? So, first, we have as we read in the metal reactivity series that there are metals who have a high reactivity, there are some metals who have a medium reactivity, and there are some metals who have a low reactivity, right? Now, first we will learn about the metals of high reactivity. We can extract metals of high reactivity by the process of electrolysis of molten ore. Now, what is electrolysis? Electrolysis is a process in which electric current is discharged in a molten or aqueous solution of a compound to extract the metals. Okay, and from there we can get a pure metal. Next is metals of medium reactivity. Who has medium reactivity? That there are two types of ore in the medium reactivity. One is carbonate ore and the other is sulfide ore. The carbonate ore we can extract by the process of calcination. The carbonate ore we can extract by the process of calcination, whereas the sulfide ore we can extract by the process of roasting. Then the oxide of metal we get, then the metal is reduced, right? Metal is reduced, and then after refining we extract the metal. Now, next is how metals of low reactivity. In this case, the first electrolysis of molten ore is done, then we get pure metal, then again electrolysis of molten ore, then again we get pure metal. Clear? So we ultimately follow the metals of high reactivity. Now, metals of high reactivity are sodium, potassium, magnesium, aluminium. Metals of medium reactivity are iron, zinc, lead, tin. Low reactivity, copper, silver, mercury. Clear? And gold and your gold and platinum are non-reactive. Now this is generally this is a metal reactivity series, but carbon and hydrogen are non-metals. carbon and hydrogen are non-metals but are included only for the reference. It is included only for the reference. Now, from lithium to silver, as we are talking about the extraction of metal and non-metals, so from lithium to silver, it reacts with oxygen, right? Lithium to lead, it reacts with dilute acid. Lithium to your sodium, it reacts with water. And the electrolysis is expensive. It is an electrolysis extraction by electrolysis, which is an expensive process. And this is extraction by metal oxide and reduction with carbon or carbon dioxide, and it is an inexpensive method. Okay. Next, as I told you in the metals of medium reactivity, that we extract by the process of roasting or calcination. So let us understand what is roasting. Roasting, that means roasting generally refers to the sulfide ores. Roasting means we follow the roasting process in the sulfide ores. These sulfide ores into oxides on heating in the presence of excess air. We heat the sulfide ore in the presence of an excess air and it converts into oxides. We heat these sulfide ores in the presence of an excess air and ultimately it gives us oxide. So it removes the volatile impurities. Volatile impurities means the impurities which can be easily vaporized. Okay, so zinc sulfide, when it reacts with oxygen, it gives, with the excess of air, it gives us zinc oxide and sulfur dioxide. Now calcination. Another was the calcination process. Calcination occurs in carbonate and hydrated ores. Okay, carbonate or hydrated ores, and it converts into oxide on heating in the presence of limited air. In roasting, we are giving enough excess air, but in calcination, we are giving limited air. Okay, and roasting occurs in sulfide ores, but calcination occurs in carbonate or hydrated ores, and both the process removes volatile impurities. Okay, now zinc carbonate is converted when in with the presence of limited air, it converts into zinc oxide and carbon dioxide. As there is a carbon dioxide carbonate, so it will definitely give us carbon dioxide. Similarly, calcium carbonate, with heat, it gives us calcium oxide and carbon dioxide. Now hydrated ore, aluminium oxide. Okay, it gives us aluminium and releases is the water of crystallization, which we have read in the last chapter. This gets detached. The molecules which are loosely attached to the compound, it get detached. Iron oxide plus 3H2O, it breaks down into Fe2O3 plus 3H2O. Clear? Now, extracting metals slow in reactivity series, which is very slow in reactivity series. Okay, which are very low, extracting metals which are very low in reactivity series. Okay, now by we can extract the metal by self reduction. Now what do you mean by self reduction? When the sulfide ores of less electropositive elements like uh, HGS, PBS and CUS are heated in air, so that the part of ore gets converted to oxide, it gets converted into oxide, which then reacts with sulfide ore to give the crude metal, so that we can get, then when it reacts with remaining sulfide, oxide, it can give us crude metal. Okay, so no external reducing agent is needed in this. In this case, no external uh, reducing agent is needed. Let us take an example. Cinnabar, mercuric sulfide, when it is heated in the presence of oxygen, it gives us HgO, crude metal, HgO, okay, and SO2. Now this crude metal, when it reacts with heat, it gives us Hg plus O, right? This is the process of self-reduction. First, when the sulfide ore reacts with oxygen, it gives us crude metal and sulfur dioxide. Now, when this crude metal is heated, it gives us metal. Okay, it gives us metal. Now, copper pyrite, sulfide. Copper sulfide is, when it reacts with oxygen, it will give us copper oxide and sulfur dioxide. Now, this copper oxide, which is a crude metal, when it reacts with this, it gives us crude metal Cu plus SO2. Similarly, galena PbS lead sulfide reacts with oxygen, it gives us PbO and SO2, and when this PbS reacts with lead oxide, it gives us crude metal Pb plus SO2. Clear? So this is the process of self reduction. Now next, active. How can we extract the metals which are in the middle of the reactivity series? Okay, by the process of smelting. By the process of smelting, it involves heating the roasted or calcined ore by roasting or calcined ore at a high temperature with a suitable reducing agent. In the self reduction, we did not require any reducing agent, but in the case of smelting, we require a reducing agent, and then thus the crude metal which we obtain, it is in a molten state. It is in a molten state. We have already read this reaction, aluminothermic reaction. Let us see how the coke, the carbon, it is a reducing agent. The iron oxide is reduced with the carbon with the reducing agent, it gives us iron plus carbon dioxide. Now aluminothermic reaction, which is also known as Goldsmith reaction, which is a highly exothermic reaction in which a metal oxide, usually iron or chromium, are heated to a high temperature with aluminum. These are heated with a high temperature with aluminum. So Fe2O3 plus aluminum gives us aluminum oxide and iron, crude metal, but it is in a molten state. Similarly, chromium oxide, when it is heated with aluminum, it gives us aluminum oxide and chromium along with it, and this chromium is in a molten state. Now, extraction of metal towards the top of the reactivity series, means the metals which are at the top of the reactivity series. In this case, we can extract the process by electrolytic reduction. By the electrolytic reduction. So the Downs process. So what is the Downs process? In this, NaCl is electrolyzed in a special apparatus. Okay. At the cathode, reduction takes place. That means Na plus plus electron gives Na. Metal is deposited. And at the anode, oxidation takes place. That means chlorine. Reduction means loses of electron, right? And oxidation means reduction means gain of electron. Sorry, I'm extremely sorry. Reduction means gain of electron. Okay, you can remember with the by the term LEO, LEO. Loss of electron is oxidation. So in oxidation there is a loss of electron, whereas in reduction is a gain of electron. You can remember by the code GER, GER. Okay, so chlorine gas is liberated. So NaCl, if you break down in an aqueous solution, it will release into Na plus plus Cl minus. Now Na plus is a cation, it will migrate towards cathode, and Cl minus is an anion, it will migrate towards anode. Clear? Now Hall's process. There is a mixture of molten alumina on fluoride and solvent, usually cryolite, Na3AFL6. Now why this cryolite is used? To lower the temperature so that it can withstand the temperature. Clear? Now an Na3AF6 is electrolyzed. At the cathode, aluminium gets deposited, and at the anode, oxygen gas is liberated. So and what is so in the so what do we learn? That in the though the metals which are in the low reactivity metal which are at the lower position in the reactivity series, they get extracted by the self reduction process, and in that case no reducing agent is required. And the metals which are at the middle of the reactivity series, they are extracted by the process of smelting, and the metals which are at the top of the reactivity series, they are extracted by the process of electrolytic reduction. Okay, now how will you enrich ores? What do you mean by enrichment of ores? It means the removal of impurities or gangue from ore. Means in an ore you can get some other impurities too through physical or chemical process. This technique used for a particular ore depends on the difference in the property. Suppose if the ore is mixed with iron, okay, so with the help of a magnetic separation, with the help of a magnet, you can separate you can extract iron from it. Okay, so this is about the enrichment of ore. Now, then you need to do refining of metals. What do you mean by refining of metals? That means you are removing the impurities or gangue from crude metal, and it is the last step in metallurgy. This is the last step in metallurgy and is based in the difference between the properties of metal and the gangue we refine the metals. It is on the basis of the properties of metal we refine the metals. Now, electrolytic refining. Electrolytic refining, you see, metals like copper, zinc, nickel, silver, tin, gold, these are refined electrolytically. Now, how we have taken in an anode, we have taken impure or crude metal, and cathode we have taken a thin strip of pure metal. That is, whatever metal we have taken, let us take, I am explaining you that copper, zinc, nickel, whatever. Now, when you will do electrolytic, when you will aqueous solution of metal salt, the in anode metal ions are released into solution, and at cathode the equivalent amount of metal forms a solution is deposited, and impurities deposited at the bottom of the anode. I am explaining you with the example. Let us take that we are refining copper. So in the cathode we have taken a pure metal, that is copper metal. Okay, copper metal is getting deposited, thin strip of pure metal. In the anode it is an impure or crude metal. In the solution it is acidified copper sulfate solution, so it will break into Cu2 plus SO4 2 minus. Now this Cu2 plus is getting Cu2 plus is getting deposited in the cathode, and this anode, it is breaking down into Cu, releasing 2 electrons Cu2 plus. So more amount of copper we are getting, and ultimately it is getting deposited at the cathode, and the impurities which are present in this solution, it gets deposited. Clear? So the reaction of M or M plus and any metal is, if it anode, the metal gives away electron. Metal reacts, accepts electron and forms a metal, and in this case it accepts electron and forms a pure metal. Let us take an example of electrolyte which I have already explained you in the last slide. That impure copper is taken cathode, and this anode is break down into Cu plus 2 Cu2 plus 2E. Now this Cu2 plus and the copper sulfate solution 2E Cu2 plus all gets deposited in the cathode, and as a result we get copper. Okay, so this was all about, and the impurities get deposited at the bottom. Now corrosion. What do you mean by corrosion? That eating up of a metal by the action of gases, moisture or acid. This is present in air. This is called corrosion. Clear? The eating of a metal. That means metal got corroded by the action of gases, moisture or acids present in air. We have taken a 3 tubes. Okay, A, B and C. In the A tube, water is there, rusty, iron nails and air. In the B tube, there is iron, air, air, iron, water and the oil. And in C there is a iron nail and few pellets of anhydrous calcium chloride, which is a drying agent. So what do we observe? This is an investigation. What do we observe? In which condition the iron rust? In tube A, both air and water are present. In tube B, there is no air dissolved in the water, and tube C, the air is dry. So what do we observe? That in which case the iron rust? In tube A, because in this tube B there is a layer of oil which prevents air dissolving in water, and thus prevents. This will also get uh, corroded, but compared to this it will get less, and in this it will not, because it has a drying agent. So now, how can you prevent this corrosion of iron? By painting, by applying grease or galvanization. Very important. What is galvanization? Process of protecting steel or iron from rusting by coating them with thin layer of zinc. By coating them with thin layer of zinc. Clear? This zinc metal is very important for this galvanization. Chromium plating or tin plating or alloying. What is alloying? Alloy is a homogeneous mixture of metal or metal non-metals. Okay. and it is a homogeneous mixture and it improves the properties of metal. It has a better properties than metals, like in case of strength, corrosion, and lower electrical conductivity and melting point. Now it is prepared by melting primarily metal first and then dissolving other in definite proportion and then cooling to a room temperature. Now the some of the example of common alloys are stainless steel, which we see in our daily life. In that there is an alloy of iron, nickel and chromium. Brass, alloy of copper and zinc. Bronze, alloy of copper and tin. Solder, alloy of lead and tin. Amalgam, and any alloy containing mercury, any alloy, okay, containing mercury. Alloy of gold contains gold and silver or copper. Clear? So I hope this video is clear. If you have any doubt, kindly let me know. Till then, please watch the video, stay at home, stay safe. Thank you.